Yes, I'm Zara and I'm a PhD student here at Monash. And as Alex said, I'm going to talk about the slow neutron capture process in binary AGB stars. Now, the slow neutron capture process, or S process for short, describes the synthesis of heavy elements through a series of neutron captures and beta decays in stellar environments with relatively low neutron flux. On the left here, I have a snippet of what is known as the chart of nuclides. So the chart of nuclides presents all of the elements and isotopes that are theorized to exist based on the neutron count on the x-axis and the proton count on the y-axis. Now, the way the S process works is that we start with some seed nucleus, such as strontium-87 that I've highlighted here, and it captures a neutron, becomes strontium-88, and it captures another neutron, becomes strontium-89. However, strontium-89 is unstable to beta decay. So before it can capture another neutron, it decays to yttrium-89 and then captures another neutron, etc. So it is through the S process that stars can synthesize elements that are as heavy as lead and bismuth. And the main source of the S process nucleosynthesis are an asymptotic giant branch stars. Now, AGB stars are stars that are born with a mass up to about 8 solar masses, and they're on their final nuclear burning phase before they eject their stellar envelopes and transition off into white dwarfs. I have here just a diagram showing a cross-section of an AGB star. So an AGB star has an inert carbon-oxygen core with an envelope, and surrounding the core, we have a hydrogen and helium burning shell. However, this is a very simplistic view, as once the helium burning shell becomes thin, it becomes unstable. And this triggers a thermonuclear runaway, which causes the star to expand and contract in what are known as thermal pulses. And it is in these thermally pulsing AGB stars that we find the S process. And the S process is thought to occur in between the hydrogen and helium burning shells within the helium intershell. Now, as the star thermally pulsates, the stellar structure of the star also changes, and mixing within the star can then transport the products of the S process up to the envelope, up to the surface of the star, where it can be ejected into the interstellar medium. And the total ejected mass of a specific elemental isotope is known as the stellar yield. Now, we should note that not all thermally pulsing AGB stars can have S process nucleosynthesis. For example, in stars that have a mass greater than about 3 to 5 solar masses, depending on the metallicity, the bottom of the convective envelope may become hot enough to sustain hydrogen burning. And this is known as hot bottom burning. And this will actually prevent S process nucleosynthesis. Therefore, it is thought that the majority of S process elements we find in the universe today originate from stars, AGB stars, have a mass of about 1.5 to about 3 solar masses. But what I'm interested in is what changes with binary evolution. So binary stars are very interesting as they have the ability to share their material. Binary systems have this thing called the Roche lobe, where within the Roche lobe, mass is gravitationally bound to the enclosed star. But should a star expand beyond the Roche lobe, mass is transferred from one star to the other, and this is known as Roche lobe overflow. Now, what happens next is very much dependent on the individual stars within the system, but should the donating star have a deep convective envelope, like it does on the AGB, it would actually expand in response to mass transfer, and as a result, the envelope of the star is stripped off and transferred relatively quickly to the companion star. Now, you can imagine this would wreak all sorts of havoc on the stellar nucleosynthesis that's within this star. Additionally, the companion star might also overflow its Roche lobe. So when we have 2 stars both overflowing their Roche lobes, we have what is known as a common envelope system, which may force our systems to merge. Now, the probability of a stellar interaction is very much dependent on the radii of the 2 stars, as well as their physical separations, but not even wide binaries are safe from mass transfer, as the stellar winds from an AGB star can get caught up into the Roche lobe and accreted by the companion star. And it is through this process that objects such as barium stars are formed. But why does this matter? Well, observations show that at least 40% of low and intermediate mass stars are found within binaries, and this 40% figure increases with increasing mass. Yet most studies that study stellar evolution and yields only consider single stars, and this includes calculations of galactic chemical evolution models, in which AGB stars are an important ingredient. So this just begs the question, How does binary evolution influence the S-process elemental yields? And is this enough to alter the stellar yields from a stellar population? So to try to answer this question, we turn to binary population synthesis. Now, synthetic stellar evolution codes are a little different compared to detailed stellar evolution codes, such as the Monash and Mason models. So where the detailed codes model their stars by solving the equations of stellar evolution, synthetic codes model their stars based on fits to the detailed models. For example, we use the code binary C, which evolves its AGB stars based on fits to the Monash models. And by doing this, we are effectively trading detail for speed. And this allows us to simulate thousands of binary star models and cover a wide region of parameter space in a relatively short period of time. A further advantage of using binary C is that it also models stellar nucleosynthesis. So not only could we evolve a stellar population, we can also directly calculate the stellar yields from that population. So what we have done is that we have simulated a population at solar metallicity using 640,000 binary models. But before I dive into the population results, I just want to talk a little about how we set up our models. Now, as I mentioned before, binary C evolves its stars based on fits to the Monash models, and we have made some further tweaks to these models. The probably most significant tweak is our calibration of the third dredger. Now, the third dredger describes the expansion of the convective envelope into the interior of the star, and it is through the third dredger that the products of the S process are transported to the surface of the star to be ejected. And the third dredger is also vital to the evolution of the AGB star. However, the efficiency of the third dredger and the core mass where the third dredger begins is relatively uncertain. And one of the best observational tools we could use to constrain the third dredger are carbon stars, as the formation of a carbon star is directly tied to the third dredger. On the right here, I'm showing what is known as a carbon star luminosity function. So this is a function that shows the distribution of carbon stars based on the absolute bolometric magnitude. Now, this yellow curve shows the carbon star luminosity function that is measured using observations of galactic carbon stars. And this black curve shows a theoretical carbon star luminosity function that we calculate from our single star binary models. Now, as you can see, it's not a great fit, and naturally we want our models to mimic observations. So by changing the minimum efficiency of the third dredger and the core mass where the third dredger begins, we are able to calibrate our models so that they better reproduce observations. But doing this has consequences, as by effectively increasing the number of third dredge-up events, we are also increasing the physical amount of S-process elements that are being ejected by our stars. So a further comparison we do is that we compare our models to observations of barium stars. Now, barium stars are main sequence or giant branch stars that have been enriched with the S-process elements, and this enrichment originates from a previous AGB star companion. Now, this plot here just shows one of the comparisons we've made, where we are comparing our models shown in the blue to observations of barium stars. So these models are of barium stars that we find within our stellar population. And all these observations, these error bars all cross over solar metallicity as well. And when we compare our models to observations of barium stars, at least through their abundances, we have a decent agreement between our observations and our models, with the exception of a few stragglers at the bottom of. So this plot shows the cerium to yttrium surface abundance of our star, and this is what we are comparing. So we managed to reproduce these abundances with the exception of a few with very low cerium to yttrium abundances. But we don't think this is a large problem for our population. So now that we have our models, we can see what happens when we put them in a stellar population. Now, this plot here shows the strontium that is ejected by our stellar population as a function of the initial single or primary star mass. And strontium, of course, is one of the S-process elements. Now, the binary fraction here, so the binary fraction describes the fraction of binary stars, or the fraction of stars within our population that are binary. So right now it is 0, which means we are currently looking at the strontium that is ejected by a population of only single stars. Now, how would this plot change if we were to increase the binary fraction? Now, doing just that, looking at this plot, so the solid colored regions show the strontium that's ejected by our population that includes binaries. And we also highlight the individual contributions from the binary primary star, from the single star portion of the population in yellow, the binary primary star portion of the population in the dark blue, and the secondary star portion in the light blue, with their sum giving us the total stellar yield from our population. The red hashed region just shows the strontium that's ejected by our population of only single stars. And if we compare these two populations, we find that the inclusion of binaries results in a 25% decrease in the strontium that is ejected by our stellar population. Now, if we take a look at a few of the other elements, so here we have barium and lead, two more heavier S-process elements. Once again, our binary fraction is 0, and we can increase the binary fraction. And in doing so, we find that we see a similar decrease in all of our S-process elements. And the main cause for this is that through binary interactions, the AGB phase is either being truncated or the star is just not entering the AGB at all. Additionally, mergers between low mass stars may cause them to begin to hot bottom burn, which will further limit the AGB star's ability to synthesize any S process. And considering that AGB stars are the primary source for half of the heavy elements that we find in the universe, including almost all of the S process elements, it is important to consider the influence of binary evolution when we are studying stellar populations. Now, these are mostly the results of binary evolution preventing or truncating the AGB, but do we find any changes in the stars that do manage to enter the thermally pulsing AGB and have any S process? So this plot here shows the distribution of our binary and single star populations, and we're just comparing them with the barium to iron abundance ratios that are ejected into the interstellar medium. So you can see if we compare the blue, which is our binary star population, to the red hash, which is our single star population, we can see that there's very little change on the abundances of our stars, comparing the single stars and the binaries, with the exception of a rare case where we have some S process enhancement. So we should note that from this work, it's very obvious that it's much easier to prevent stars or to hamper the S process than it is to enhance it. However, all of our work at this point has been at solar metallicity, and to gain a more complete understanding, we need to explore lower metallicities, as this gives us more options for both observational sources to compare to and just give us a more general outlook at the impact of binary evolution on the S process. So that's all from me. Just a quick summary before I let you all go. So we are using the binary population synthesis code to examine the influence of binary evolution on the S process elemental yields ejected by a population of low and intermediate mass stars, which eventually evolve into AGB stars. And we find that at a fraction of 0.7, our S process yields are all reduced by 25% in comparison to a population of only single stars. So if you're interested in the details, I do have a paper that will hopefully be submitted in the next few weeks. But anyway, that's all from me. Thank you all very much.
Thank you, Zara. So thank you for the talk, for the presentation. And you mentioned that in some cases you got some enhancement of the barium production. Yes, exactly. So where does it come from? What is the reason behind it?
So one of the things that controls the amount of S process reactions available are the number of third dredge-up events. So in some stars, when they interact, they can gain mass and actually have more third dredge-up events, and they sit on the AGB for longer than they normally would while single. So they have more thermal pulses, they have more S-process nucleosynthesis, but it's quite difficult to get a star into this position.
Thank you.
Hey, I was interested in your calibration to the carbon stars. So when you were showing the original, this plot. So do you have to worry about any selection effects when doing this comparison of like the theoretical model to the observed population? Like, is there?
So we are using single stars for our calibration, and in the ABIA 2022 paper, they do have like a sample of carbon stars that they believe to be single based on their luminosity. So there might be some, intruders in there, but I reckon that the overall it should be okay. Like there might be some selection effects, but I don't think they will have a large impact.
Yeah, I guess I was just also thinking about like just the fact that the fainter stars are harder to see, for example.
Oh yeah, I see.
So they might not be in the observed sample, but your model might say that they exist or whatever.
We do have some fainter stars in our model, but yeah. I don't work on the observational side, I'm sorry.